So it's really the role is about, and the team is about making our systems and our technology more available for researchers and the research community, as well as the academic community for education. And I'll give you some more insight into how we do that once we're done introductions.
Awesome. Next person is Ali. Please introduce yourself. Ali, you're on mute. Ali, are you on mute? Yes.
I am. I'm not now. Thank you.
Yes.
Thank you so much for your persistence in finding me to my email. I really appreciate it. And Sebastian, I love the work that you guys do on IGC. I think it is fabulous. Everybody developing it here. And I'm in stealth mode right now, so I can't really say much about what we do, but we're ready to build up quantum machine learning on the hardware side. So that's where we're at.
Thank you. Amarendra Mishra. Amarendra Mishra.
Hey there. Hi everybody. I work for Chase and I work for Constantine, inshallah. I know a little bit about quantum, not a whole lot. So I'm just trying to know or understand a little bit more. Thanks.
Awesome. Thank you. Andrew T. Andrew T.
Andrew Torres, it's me. Hello. I'm glad to hear everybody. It's nice to meet you. I'm a business development manager at Quantum Machine Learning Project at Russian Quantum Center, and I'm here just for listening and new knowledges and to meet everybody. First meet. Do you hear me? Hello.
Yeah, it looks like Alexei might be. We heard you definitely. So Alexei may be having issues again. So let's do Jacob Mendel, please.
Hi, good morning, everybody. Good evening, if you are from the other side of the world. I'm from JPMorgan and working for Dr. Marco Pistoia.
Welcome.
Thank you.
Arunangshu Debnath. Arunangshu Debnath?
Yes. Do you want me to introduce myself?
Yes, please.
Okay, so hello everybody. I'm a researcher at German Synchrotron, which is abbreviation is DESY. We call it DAISY. It's in Hamburg, Germany. And I do research on mostly quantum dynamics and how to do multidimensional spectroscopy with entangled photons. So I'm a theoretician, so this is the branch of my research. And I'm pleased to join the event.
Very cool. Welcome. Welcome. Vitaliy.
Hi, my name is Vitaliy Dorum. I work for JPMorgan. I work for Constantine actually. So I'm a software engineer. I was previously a software-defined networks engineer, and that's my spiel in terms of what I do.
Awesome.
And the rest is going to be via demo.
And the rest will be history. Thank you. Alexander Batz.
I'm from JPMorgan Chase. I work for Marco, and I'm software engineer currently, but I work on quantum algorithms with Marco.
Great. Welcome. Konstantin.
Yeah, I'm with JPMorgan Chase. I lead a team called Advanced Computing that, among other things, includes quantum computing since 2 years ago. And we also do, cloud, machine learning, and all of the rest of the advanced stuff.
Awesome. Thank you. Austin T. Gilliam.
Yeah, hi, I'm Austin. I'm a software developer and a researcher with a background in machine learning and now quantum computing as of about 2.5 years ago. And I work with Konstantin and Vitaliy and Marco Pistoia.
Great. Welcome. Harshita Gandhi.
Hi everyone. I'm Harshita Gandhi, and I am an undergraduate student. I'm in my pre-final year, and I'm here to get to know about quantum and probably make it my career. Thank you.
Great, welcome. Indra Nilday.
Hello everyone. I work in JPMorgan Chase as a software developer. Recently, I got introduced to quantum computing through one of the sessions by Marco, and I am very happy to be involved here and listen to you on this field which I am currently exploring. Thank you.
Oh, you might have lost Alexi again. Let's see. How about Greg?
Hi guys, so I work in the areas of big data, artificial intelligence, and machine learning. I'm interested in applying quantum computing to probably maybe distributed systems. I also want to write maybe a quantum algorithm at some point of time. Yeah, thank you.
All right. Jacobo Roy Vicens.
Hello, I'm a member of the Machine Learning Center of Excellence in London, working in JPMorgan for Chuck Wong. Looking forward to learning more of quantum computing in applications to machine learning.
Thank you, welcome. So as you guys noticed, some of our connections are unstable. If I'm pausing, Sebastian will take over leading the introduction, so don't worry. Jamie Gill. Jamie Gill.
Hey Lexi, I'm Jamie. I'm out of Wisconsin, student studying quantum computing at the graduate level, and excited to hear about the whole financial applications aspect and what they're doing over there.
Awesome.
Okay, how about Hargun Kalsi?
Hi, I work for JPMorgan Chase, and I work on engagements for the Future Lab of Applied Research and Engineering with Marco Pistoia, and I have very minimal knowledge on quantum, so just here to learn and listen. Thank you.
Thank you. Marco Pistoia.
Hi, everyone. I work for JPMorgan Chase. I lead the Future Lab for Applied Research and Engineering, also known as FLAIR. You guys have heard a lot of people from my team here, and I lead the quantum computing effort, the research effort at JPMorgan. Thank you.
Great to see you, Marco.
Thank you.
Hey,
Thank you.
Sebastian, good to see you again.
Michael Baynard.
Hi, I work for JPMorgan, and I'm just here for informational purposes, being sort of newly exposed to the quantum computing paradigm. So I'll just be listening. Thank you.
Okay, looks like Alexi might be frozen again. How about Nick Braun?
Hi, I'm Nick Braun. I've been in experimental quantum computing at IBM since 2013. Currently work on hardware engagements with startups, academic groups, companies, and education and training.
Great, thank you. Rajesh Narasimhan.
Hi, everyone. I'm a software engineer from JPMorgan Chase, and I work with Konstantin and Austin primarily on cloud and machine learning technologies. Here to just learn how quantum computing is combined with cloud technologies. Thank you.
Welcome. Ricardo Carrillo.
Hey guys, Ricardo Carrillo here. I'm a junior engineer working for JPMorgan Chase, and the quantum and ML team in digital advanced computing decided to take me under their wing. So I'm here to absorb as much information as possible, just to try to get useful in what they're doing.
Awesome, welcome. I think we're all learning, so this is really great to have so many folks learning this field. That's amazing. Sahana.
Hi. So again, I work for JPMorgan and Chase as a Java developer with some ML background. Quantum is something that we've just started exploring. So yeah, here to learn more.
Great, welcome. Susie Shan. Hi, Susie. You're on mute, I think.
Oh, sorry. Yeah, so I'm a Java developer. I'm just listening in, try to get some information.
Awesome. Welcome, Susie.
Thank you.
Sandun Pathangi.
Hi. Yeah, I'm here merely for my curiosity to learn. And I'm a data architect with JPMorgan. But I'm also starting school at Johns Hopkins in end of August for applied physics. So wanting to learn more about quantum physics and quantum computing. So
great. Welcome. Let's see, Simon Ewing.
Hi, my name's Simon Ewing. I'm a graduate level theoretical quantum chemist. So I'm working in an area called reduced density matrix theory. So it's only tangentially related to actual quantum computing, but I'm excited to learn more.
Awesome, welcome. Joachim Skor.
Yes, hi. I'm also at JPMorgan Chase working in model development and interested in quantum computing entirely out of my own interest. Thank you.
Sounds great. And you have a lot of interest. I see you have a piano in the frame, which is great.
Sorry about that.
Oh, it's awesome. It's fantastic. Vasily Nechayev. Vasily Nechayev.
Yeah. Well, guys, yeah, I'm a software engineer at Crunchbase with financial background and interested to learn about quantum computing and its application in software engineering. Yeah.
Great. Welcome. Vinit Shah. Vinit Shah.
Hey, hi. So I'm an employee of JPMorgan Chase. I'm into architecture and design authority space, but I'm keen interested in this quantum computing, going through Constantine and Austin papers, as well as Marco Pistoia videos and papers. So yeah, I'm pretty much interested in this space and trying to get information out of it.
Great, welcome. VGG, I think Veselin Georgiev.
Yes. Hi, Alex. My name is Veselin, and I just entered the channel. So you kind of quickly noticed that I arrived. What are we doing?
Oh, we've lost Alexi's sound. Just a quick intro. We're all just introducing ourselves.
Oh, okay. So my name is Veselin Georgiev. I'm located in California, more precisely Central California. My background is physics, and I've done nuclear physics and computer modeling. And recently, I'm interested in quantum computing because this is a great tool for me to continue my explorations of quantum physics and nature.
Great, welcome.
Thank you.
And you, son?
Hi, everyone. I'm with quantum research at JPMorgan Chase. I'm working on quantum computing with Marco, Constantine, and Austin. Glad to be here.
Great, welcome. Zhiyong Zhang.
Sorry, I just muted myself. Hi, everybody. My name is Zhiyong Zhang, and I'm working at the Stanford Research Computing Center. And my background is in high-performance computing and computational chemistry. And recently, I have been working on a new quantum computing algorithm for quantum chemistry. Thank you for this great opportunity for learning more about quantum computing.
Thank you. I'm not sure I caught the audio, but it's maybe my connection.
Yeah, we heard it fine.
Great, thank you. Apologies, guys. It's yeah, you never know, right? This is the uncertainty of our online times, but we have a lot of good folks here who can ascertain everything's going well. So I think at this point, if I missed anybody, please introduce yourself. Feel free to. We open the floor for the rest of the introductions. Feel free to speak. Let's see if this will work. Or you can also mention it in the chat and I can read your name, whatever works for you. So I'll just wait a moment for anybody we missed. Just type your name in the chat and I can introduce you. If not, I think we will proceed to the next item. So we're very fortunate to have with us Sebastian Hassinger, who is the lead of academic programs at IBM. And basically, he thought of this quantum conversations. It was his idea. We did a lot of things together in previous lives. And he will say a few words about his work.
Sure. Thanks, Alexei. I wouldn't say it's my idea necessarily. I feel like this came out of conversation with you. So I run the academic partner program for IBM Quantum. There's a lot of, it's very simple to sum up what our mission is, but it's also very complex to explain all the ways in which we're doing that. Very simply put, we're trying to expand the community around the IBM Quantum platform and technologies to include education, researchers, industry, and increasing the general level of awareness and knowledge about quantum computing. Now, translating that into programs and offerings is a couple of slides worth of tons of links. So, I would say it's interesting, actually, this workshop, this particular session, it's great to have so many partners from JPMC. This puts more of an industry partner slant on it. But we start sort of with learning resources and educational resources. We've got a tremendous resource in the open source textbook and the YouTube channel, as well as self-paced tutorials and stuff on the IBM Quantum experience. So whether you're self-paced learning or you're looking to set up a class in a university or actually in industry as well, we've got all sorts of resources that can be used to support those activities. We're also developing actual offerings ourselves. We have a group called the Skills Academy. They have a first quantum computing offering, which is sort of a turnkey solution for delivering sort of an introductory cross-disciplinary view of quantum computing. So it's a starting point for institutions and firms that don't have existing capability. We'll be adding more to their offerings so that there is, we actually are working on a quantum developer certification test, and we'll be building almost a preparatory class that will be able to be geared towards that certification test, and that's all coming up in 2021. So there's a ton of activity around education. The other sort of focus is around research, which is probably more cogent to this particular audience. So obviously there's institutional access through the Q Network membership. JPMC is a member of the Q Network, and that gains you access at an institutional level, site-wide level, to all of the private resources that IBM has, the 53 qubit machines, the 27 qubit machines, open pulse, dedicated reservations, as well as other support and content. But then that's kind of the commercial offering. What my team is doing is try to create programs that get access to individual resources at the researcher level. So if you're a researcher that's affiliated with an institution that's not part of the Q Network, or you're not part of a project that's at Oak Ridge, for example, or other ways to gain access to the Q Network, we're trying to make it easier for researchers to be able to gain access to open pulse on a larger qubit machine, and in some instances, the larger machines where needed for supporting a particular project. So in July, we'll be actually launching a couple of web pages that will take applications for membership to the IBM Q Experience for Researchers group, which is a higher priority queue on the public machines, as well as machines that are not available to the public, and also a private Slack channel for sort of talking amongst yourselves about how to use these systems, and also access for projects, which if a project requires open pulse or pulse level control, whether you're looking at gate design or error correction or simulations or other applications of the microwave pulse control, we can grant you access on a project basis to a 5-qubit machine using open pulse. And if you haven't checked it out, open pulse is available to the public, but it's on a single qubit machine. So you can get a sense of what you can do, but it's limited in the applications, obviously, because it's just a single qubit. And in addition, actually, on the education front, the third program we're launching is if you're a professor that's using the open source textbook, we can grant you access to a group that has access to that 5-qubit open pulse machine, and that you can provision your own students onto that group, and also schedule dedicated time on that system, so that if there's coursework or classwork that requires faster turnaround on the queue, you can actually line up that dedicated access with your class time. And in addition, there are other programs we run, like the PhD fellowships, which are coming up in mid-September, and also faculty grants for being able to award financial and in-kind services for projects that we support. So there's, as I said, a large number of ways to get engaged. The overall, as I said, the overall mission is really just to expand this community. I think that from my perspective, just sort of to close out my comments, I think that we're in this really fascinating time right now where you've got basic fundamental research going on, as well as the early stages of commercialization and the attempt to build the infrastructure that we need in order to develop the workforce that we're going to need as industry clients, as IT vendors, and as academic institutions. So there's a number of challenges right now that really IBM's view is that the best way to tackle those is as a community and as partners and is with as much open collaboration as possible. So that's really our approach to building the community, and that's the essence of this workshop, is really to start having a regular check-in that people can start to develop connections, get exposed to new ideas, new work, and in a more informal way. Back to the starting, the conversation with Alexei, what I really liked about what Alexei had done was that he brought the data science and AI community together in the Bay Area in a way that was highly collaborative, and a less formal way that I think can be a little bit less familiar to the hard science research community. And I think there's a lot to be gained by sort of cross-pollinating those industry players with the research, with the IT vendors, in a more interactive fashion, so we can really start to get to know each other, what work we're doing, and find ways to collaborate. So welcome.
Thank you, Sebastian. Thank you, Sebastian. Really appreciate it. And yes, I think this idea was really a result of the collaborative brainstorming we did in the coffee shop. We remember there were coffee shops in the previous life, and so in the Blue Bottle. And originally we wanted to make it a physical community, Quantum West, right? Because the East Coast is heavily represented, but the West Coast is not so much in the community space, right? And around by the Bay conferences and meetups, as Sebastian said, and we really have great community spirit. So most people come back and say, this like 30–40% of the people in the conference stay in the hallway. So there is a famous hallway track. They meet each other and establish these lateral connections. And I found when I go to academic conferences, this is often missing because it's a bit hierarchical. It's a top down, and it's a great culture. But we want to kind of spruce it up and introduce computer science influence in it, which is this kind of bottom up graph of connections, which builds by collaboration. So
yeah. And Alexei, just before you turn it over to JPMC to present, you may want to give somebody else co-host, because I'm going to have to unfortunately drop at the top of the hour, so a little over 30 minutes.
Sounds good. Yes. So I'm gonna probably yes, I'm gonna I mean, what I'm gonna do, I'm probably just give it to Konstantin, and he can hand it off.
Yeah, or I think Austin would be a good choice.
Austin, okay, so I'll find Austin and give
He's
it
our backup in case something happens.
Great, great. Yeah, you guys come prepared. I really appreciate it. And so, Sebastian, one more question for you. If folks want to contact you about the program, what are the best ways to contact you? And I can share it later with the list.
Yeah, just email me is fine. I mean, I can share that slide with the links so you can explore those links. Actually, you can share that to the group, Alexi, afterwards. All those links are live. So if you want to explore what's available, that's a good starting point. If you have any questions, just email me.
Great. So, so basically, just send me the slides, guys, and I have the list of all folks who register. So I will forward the slides, the questions. But if the slides will be available, and if Konstantin will make their slides available, I can share that as well, right? So basically, anything speakers care to share, we'll share later through the mail list. And obviously, Quantum SV is our website. We mirror information there. So this is where the videos appear after the meetings, and so we'll put the video there as well. And if you're looking for something and don't know where it is, just email me. My email is there. It's alexi@chiefscientist.org, and so I'll try to find it for you. Thank you. Okay, so now we are going to hear our main talk. It's by the JPMorgan Chase group, and Konstantin is a speaker we know well in the Scala community. So I think it's really great to have someone who straddles so many different worlds. So he did the talk on basically quantum computing and Scala, and I remember vividly when it appeared, it was the most unlikely combination of all things you can think about. But on the other hand, I think it's a likely combination because Scala has this mathematical quality to it, which appeals to a lot of scientists. So for instance, a lot of natural language processing is done in Scala because the kind of folks who do NLP tend to choose Scala for its conciseness. And I think it's it's almost like mathematics. So I found that a lot of folks who were trained as physicists and mathematicians gravitate towards it. So I think it's really great that it found its way into quantum and in broader context functional programming. So to me, this is an amazing achievement that Konstantin is able to do things like Scala and quantum in a bank. And it's really interesting how this all applies to fintech. So welcome, Konstantin. Take it away.
So you can see my screen?
Yes.
Okay, so I should say that we are partners with IBM. IBM actually helped us get started 2 years ago in quantum. We still have that partnership and we meet regularly and so on. We have papers, published in collaboration. So that's always great to see IBM people here. So this is about simulators, right? We asked Alexi, do you want a purely quantum talk or something that's combined with computing? And he chose this one, right? So why simulators? When you run a computation on a real quantum computer, that's pretty expensive, right? So one reason is you need to prepare and make sure that you have everything is verified, it's correct, and so on. But we found also that simulators are a good research tool, right? So you can just poke to the quantum state and find patterns or some insights that otherwise you wouldn't see them. And that's why, I use Scala as well. We actually had a Java simulator. Of course, we have Python. And one thing we found out, it's a very good tool for research. And we actually create simulators specific to a problem now, right? So we'll talk about that a little bit. And in this case, because we were looking to distributing and having as many qubits as possible, we chose Go and Kubernetes. But writing, a simulator, as you'll see, is not very difficult. So first of all, quantum computing is very good at solving exponential type problems, right, that classically are very hard. And I'll just use a simple Ising model, or Ising if you are German. So that the model is basically you have a number of sites that you can think of them as magnets. And then magnets can have the north up or down, right? And this is an exponential number of configurations in terms of number of sites, because each magnet can be up or down, right? And then if you want to investigate these configurations, then it's a very hard problem. And quantum computing is very useful in this kind of context. And for such a problem, you define a Hamiltonian, which assigns to each configuration an energy. It's based on the weight of each interaction between magnets, and you can add, this gives you a quadratic part, and then you can add interaction with the environment, and that's a linear part. So throughout the presentation, I'll use this simple example, and the interactions will be only between neighbors, magnets that have a north pole up. So basically, it's the number of neighboring magnets or sites with a north pole up, right? And so we are interested in investigating ground states, which means what's the minimum energy configuration. Right? In this case, it's no neighbors should have the north pole up, because then you get 0, right? So those are the ground states. How many are they, and how do you get them all, right? And so on. So this, I just chose a very simple example. I'll pause from time to time to ask for questions, but if you feel like I should clarify something, please let me know. What is quantum state in general, and how do we represent it in a program, in a simulator? So we are not trying to address quantum mechanics here. Quantum computing is simpler than quantum mechanics, right? So for example, in quantum computing, you only deal with binary strings as outcomes, and it's called the computational basis, where the basis is formed of the binary strings of a certain length, right? So this obviously matches, the view of computer science, where everything is based on zeros and ones, and that's where quantum computing is connected with classical computing. We're not interested in other kinds of computational, other kinds of basis, or other kinds of quantum state, right? Or even we're not interested in, for the purpose of this talk, how it's implemented in a real quantum computer, right? So with that being said, the quantum state is very simple. It consists of pairs of outcomes and complex numbers called amplitudes for each of the outcomes, right? So for example, if my space is 3-dimensional, or I have 3 qubits, then I have 8 possible combinations of zeros and ones. And to each of those, we associate a complex number called amplitude. And that's it. This is a quantum state. With the constraint that the squared magnitudes of those complex numbers, they add up to 1. Right? And with this, that's all we need to say about quantum state from the quantum computing point of view. Right? Pretty simple. This is a spreadsheet, basically, right? So another useful thing we found out when we play with quantum state and quantum computation is we need to visualize what's going on, right? And we came up with this idea of associating a color to a complex number. So basically a pixel, if you want. The hue of the color is the angle, the phase of the complex number. And the saturation is the magnitude, right? So the more intense, the longer the absolute value of the complex number, the more intense the color. And of course, this is not new. Complex analysis is using this for some time, right? But the application in quantum computing, we were surprised to see that nobody else did this, and actually we are contributing this into Qiskit, which is the IBM framework. And IBM has a few types of visualization. This, the next release, right, Austin? You are working on that?
That's what we're targeting, this major release.
I think IBM has color histograms. This was our first idea. Why don't we color the histograms, right? So it's already there. Now, in terms of colors, we start the real numbers are red because you start at the x-axis and then you rotate, right? I think IBM chose blue for the histograms because the normal color is blue, and then, or maybe because it's IBM, and then you know, it rotates a certain way. So colors are a code basically. And since we're talking about outcomes, when you have a quantum computation, I guess most people know this, but I'll just mention it for the people who may not. You get, when you measure, you measure the quantum state is collapsing to one of the outcomes. So you'll just see that outcomes, a bunch of zeros and ones, a binary string. And then that quantum state is basically destroyed. It's a classical state. So you can create it again, you run it, and you get another outcome, right? And then another and another and another based on the length of that amplitude. You know, the probability is the square of the magnitude, and this is called the Born rule. It was a pure intuition on part of Born's, you know, when he created this rule. Initially, he thought it was just the magnitude, but then he found out it's squared, right? So it's very similar to a slot machine, if you want. So when you pull the lever, you create a computation and then you measure it, and you get one of, you know, the binary strings, and then you do it again and again and again, right? And if you build another image with the pixels that you got, you know, because each of these can be mapped, you know, they are the keys of the pixels, then you get a sort of gray image of the intensity, right? That's how you can think about it. It's useful since this is sort of a strip, you know, a column of pixels. We like two-dimension in general is easier for us, right? You can make it n-dimensional if you want, and that's the real quantum state if you want, it's n-dimensional, but the best for visualizing it is if you make it an image. So you have 2 dimensions. So you basically split your amplitudes into columns. And to make it nice, we usually make it by prefix. So each column has a prefix, and then the others are the suffix of the binary string. So this way, the quantum state really becomes an image, right? It's not an analogy. It's really a one-to-one. You can think of, you can convert a quantum state to an image, and if you work hard enough, you can convert any image in a quantum state, right? But you have to normalize it. So intensities add up to, you know, the squares to 1. How do we represent this in code? So we use Go, and it's essentially an associative array, right? Like a Java map or a Python dictionary, all of those will work. What we found out in Go, if we use the Go map, you know, the built-in, it has concurrency built into it. So when you add a key, you remove a key, it will complain, right? Here you don't need to add keys or remove keys. The keys are always the, you know, the binary strings of length n, 2 to the n, right? Always. So then we don't have concerns about concurrency, and a binary tree works great. So that's what we did. Basically, took the implementation from programming 101. You know, you have a node and the tree, and that works great. So if you take a binary string, you follow the path, like 0, 1, 0, 1, 0, right? You follow that path, and you get the amplitude, which here is 0.02 plus 0.09 times I, right? The values are in the leaves, the amplitudes. What about any questions so far about the representation, basically a map or dictionary? Okay, so what about a qubit? Everyone is talking about a qubit in, you know, in quantum computing. How do we represent that? Well, we don't need to, because it's just a position, right, in the binary string. There is no entity or something like that. So in physics, you have an entity, right, a particle, and you act on it, right? But that gives us a dimension. That's how you have to think of it in quantum computing. It's a dimension. So in math, you know how to apply, you know, operations across a dimension, and that's what a qubit gives you, is that position. So there is no special representation. For a single dimensional, one-dimensional system or a single qubit system, it's just two pixels or two complex numbers, right? Associated to 0 and 1. And that's it. This is a, a qubit is a dimension. And what are the single qubit gates or the one-dimensional gates? You've heard of Hadamard or X, Y, Z, and so on, right? A gate is just a function, right? That takes two complex numbers and replaces them with other two complex numbers. That's it, right? So those two pixels, you trade some intensities and colors, and you get two new pixels that will replace the previous ones. And that's all there is to a gate from the computational point of view, right? And the basis gates, in general, like in any instruction set, in any kind of computing, like RISC and so on, you have a set of basic instructions, and the rest are derived. In quantum computing, you can work with H, Hadamard, and the phase gate, and everything else is derived. And the implementation here in Go, you see how the Hadamard is basically, you have two complex numbers, A and B, you replace them by A plus B and A minus B, normalized, because they need to, the squares need to add up to 1. So you replace two numbers by their sum and difference, and that's Hadamard. The phase gate rotates the second one. So you multiply the second complex number by another complex number, which means that you rotate. And that is a unit complex number. So you multiply by cosine theta plus I times sine theta. And that's phase, the phase gate. And here I can run an example. So in the initial state, we start with a state that always gives you 0, 0, 0. In this case, I have a single qubit, so it gives me 0. That's why you see the highest intensity, and it's red because it's a real number. So we always get 0 in the initial state. It's basically not a quantum state. If you apply Hadamard, you'll get a superposition where both 0 and 1 are possible, right? And the probability is the same. That's why the colors are the same. It's a little bit less intense than the previous one, right? The probability is 0.7 and so on. Is 1 over square root 2. And then if you apply a phase gate to this one, you'll see the second number changes in color. So that means you multiply it by a number. And I can run something in the IDE. Any questions so far? So I can run this, let's look at the code. So I want to have just one qubit, one dimension. And then I'm applying the H gate to, well, it's only 0. I can have multiple qubits, right? And then we'll get an image here. If I run it, and I'm saving to an image, and that image is here, right? And you can see we got the same. Let's see if I use 2 qubits. Sorry, I need to get to the image. Yeah, you see, so now it has 4 pixels, and I can actually make it 2 columns here. If I want, I can. It has to be a power of 2, but otherwise you have freedom. And now it's a different shape, right? So this is what the simulator does for H. You can play with it, understand it better, right? And now let's take the phase. So the phase, I have another test for phase, right? I'm doing a Hadamard first because otherwise, if the second qubit is not active, I won't get anything, right? So I do Hadamard first, and then let's say 3 pi over 8. And if I run this, I'll get this picture, right? Let's change the, let's make it, I don't know, 3 pi over 4. Look at the image. Is it the same? Oh, okay, I have an error. Oh, it didn't take the change. Okay. Let me try just pi over 4. Yeah, and you see a different color. So that's how the phase works, and I can, you know, I can use multiple bits, right? So it's already, you know, giving you an idea about what's happening. Any questions so far? So the next thing is the other gates, the other one-dimensional gates. How do we implement them, right? So if you have H and the phase, you can implement the rest. IBM actually uses, instead of H, it uses Rx pi over 2, which is similar to H. So it still takes the sum and difference, but it rotates them. It's a multiplication by I in each, you know, each of the amplitudes. And other systems, they, for example, Honeywell uses different, or trapped ion, right? They use different bases in Rx and Ry combination and Rz, right? So the beauty of a simulator is if you work with a different hardware, then you can adapt. You can put new gates in, right? It's as easy as adding. You saw the Go code there. And after that, you can build Rx, Ry, Rz. I have, you know, my notes here, but they're not hard to derive. For example, X. X is just swapping the two amplitudes. You have A and B, and then you return, you have to swap them. And the Z, you just change the you know, sign in front of the second amplitude, right? And with a simulator, you have a choice. You can do this, and you have a shortcut, or you can build them from the basis gates, and then you are more like a transpiler, right? Again, you have a, depending on the goal of the simulation, you can take some shortcuts if you need to. What about multi-qubit gates, right? So how do you transform quantum state in general? And the answer is, you don't need any 2 to the n by 2 to the n matrices. So that is, matrices are useful in linear algebra when you prove something or you read proofs, right? But you cannot apply them to a real computer. The only thing you can apply to a real quantum computer is a single qubit gate, right? That's it. So then the simulator should do the same, right? Of course, you have control gates. We'll talk about those. IBM has a third, which is the CNOT. So how do you apply a single qubit gate to a multi-qubit system, right? And the answer is that you pair the amplitudes. So you choose a target position, and that's your qubit, right? Let's say the middle one here. If I have a three qubit system or a 3-dimensional system, the outcomes are binary strings of length 3. So if my target is the middle, then I pair up the outcomes in such a way that they differ only in the middle position, which is the target, and the rest are the same, right? 0, 0, 1, 0, 1, 1. And then I apply the gate formula, whatever it is, X, Y, Z, to those pairs, right? So the single qubit formula, I apply to these pairs, right? So this changes all the amplitudes, right? It's a huge amount of computation, right? If you have billions of amplitudes. So a single gate application in an n-dimensional system changes everything, right? And this is the power of quantum computing, right? Physically, you apply it to a single particle, right? But computationally, you change the whole, you know, billions of numbers. And classically, this is very hard. So that's why the simulator will take a lot of resources. And the converse is true. So in a quantum system, it's very hard to change a single amplitude, very hard. Right? But classically, we just go to the record and change it in a database, right? So this is the main difference between classical and quantum computing. Quantum computing is multidimensional. So what we can say, by these pairings, what we do is actually we just have a for loop. We go through all the amplitudes. Let's say we look at those with 0 in the target. We find the pair, and then we just apply the formula, and that's it. This is the only computation you do, but you do it, in a giant for loop. So quantum state transformation, a unitary, if you want, is just a for loop. You can, you can unfold matrix multiplication into for loops. In my talk, in Scala, that's what, that's another way to look at it, a monadic approach, right? Any questions so far? So now what is a control transformation? In a physical system, this is entanglement, right? And it's very difficult to do it. But in a simulator, what you do is actually you restrict the application of a gate to those outcomes that have something fixed in some position, like 0 and 1. You say first position has to be 0, third one 1, and I only apply my transformations to those. Classically, this simplifies the computation, right? So it's a shortcut that you want to take in a simulator. In a quantum system, on a real computer, this is very difficult. So the number of controls actually kills, if it's a high number, kills the coherence. But in a simulator, this actually helps, right? So again, depending on your goal, when you simulate, you can take some shortcuts, and this is one of them. If you want, you can, have ancillas and so on, but you don't need to. You can even match zeros, right? Not only ones. So IBM has an additional gate called C0 or control X to do this. So in the tree interpretation of an implementation, we have this in code. So everything I'm saying is in code, right? And you can implement a simulator in 100 lines of code, and you'll get the same results you get on a real computer, right? So these simple concepts, pay off, and also help understand, quantum state in general, maybe even in nature. So if you control on the middle qubit and you say, let's say you want 1 there, in the graph, in the binary tree, you only look at the paths that go through 1, right? So only those states will be affected. That's the interpretation. Now, in terms of circuits, I have an example here. So a circuit, is represented by a wire for each qubit, and then you put gates, single qubit gates on those wires, and they also can be controlled, right? That's how we represent. What I have here is we apply to the bottom right. We apply a rotation around the y-axis of the angle pi over 2 to all the qubits first. This will put them in superposition. So now each of them will maybe measure the 0 and 1. And it's also equal superposition. So then what this circuit does, going back to the Ising model, where I said we don't want neighbors to be 1. So if the first qubit is 1, I'm undoing the superposition. So I'm rotating back by negative 90 degrees. So this way, the second qubit will measure 0 if the first one was 1. So I'm ensuring that you don't have neighbors, that are 1, pairs of consecutive ones. So we do this on our qubits. And so this is an implementation of, what I mentioned, that Ising model, simple Ising model. How do we represent this? And I'll run this circuit. How do we represent this? Well, a transformation has to have a target, has to have the gate, and also a number of controls. I'm allowing 0 and 1 to say, in these positions, you want 0 or 1, right? And that's it. After that, the state, actually, I made it an alias of 3, and adding these methods where you apply a gate, and the apply methods are just for loops, where you pair up amplitudes and creating new amplitudes. Yeah, before running the circuit, I'll make another connection, which is more than a connection. So any quantum state is an image, if you visualize it like this. And in Go, by the way, I'm using a pixel, really pixel. So this becomes an image using the Go language that represents the quantum state. So any quantum state is an image, but if you evolve the quantum state through gates, right, you'll get multiple frames if you want. So a quantum computation is actually, you can think of it as an animation. Again, it's not an analogy, it really is. If you put together the frames, you'll get an animation. And now anything you know about computer animation applies to quantum simulators, right? Because you can distribute state. So in a computer animation, all the pixels change, right? The same is true. It's a huge amount of computation. You also have strict rules about what you do, like ray tracing or whatever, right? Here we have gates. But I would argue that quantum computation is much simpler. It's probably the simplest kind of computation, so where you just, change two numbers. And as a reference, a 4K frame corresponds to 23 qubits, a 5K to a 24. So it's just one more qubit. This gives you, again, the idea of the power. You add one more qubit, you double the resources that you need in terms of memory, network, everything doubles with every single qubit, right? So we'll be able to simulate, to some extent up to 20 something qubits on a single machine. But then if you want to scale, that's why we're using Kubernetes, right? And so you can add 10 qubits with 1,000 containers, 1024. But if you want to add 20 qubits, you'll need 1 million containers, right? It's not easy, but it's doable if you really want it. What we did first in Go was just to parallelize using Go routines, and that again pays off depending on the number of cores you have. So you assign sub-tree to each Go routine, right? And you really get a speed up. So that was the first step. Then we partition the state. And then, let's say columns. So each prefix corresponds to a column. And then that column is managed completely by a process, right? In terms of memory, storage, if you want to do storage. This later will become containers, right? And the nice thing about this prefix-suffix partition is that when your target for a gate is a suffix, everything stays in that column. So everything is local then. If the target is a prefix, so again, you have to match pairs that differ only in that target. It means that the prefixes will differ only in one position. So that means that you are pairing up two servers or two columns, right? And all your pairs will be between those two. So it's a perfectly symmetric computation, right? So first of all, you have to, if you can, stay in one container. So if your targets are suffixes, right, and you can reorder your qubits. Let's say if you know for sure that 20 qubits are not targets, they are ancillas, then you make them prefixes, right? And you'll only have local computations. You'll not even have distributed computing. So that's one of the optimizations. So Vitaliy will show how we'll do this in containers. And going from a simple state to a prefix state or a column is very simple. We wrap the state, but we need to find the other container or column that has the pair. So we need this amplitude store resolver, we called it. So let me run this circuit now, right? And here we are actually revealing that Ising model is related to Fibonacci numbers. So if you look at how many binary strings have no consecutive ones, that is a Fibonacci number, and it's interview question sometimes. right? So this circuit actually will only produce binary strings with no consecutive ones. And if you count, it will be a few. For example, here for 3 qubits, we have 8 pixels, right? And you can see 3 of them are white. That means they're not possible. The other ones are possible because they have no consecutive ones. Right, so, and I'm showing how we run in 1 process or 2 processes. So let me do this in the IDE. And I guess we'll have to speed this up a little bit. How are you doing with the time, Alexei?
We're fine, right? I think we're flexible, so feel free to, you know,
okay,
go
cool.
as you need. Yes.
So this is the, it's called, the test is called test heuristic. So it's heuristic because you saw how we came up with that circuit. It was more like an insight. Oh, let's put it in superposition, then let's cancel the superposition, right? It's not a canonical or, you know, automated way to do it. And that's one of the, you know, beauties of quantum computing and what's more difficult, even though what I'm showing here is that the state is pretty simple. But what gates to apply, that's the really, you know, hard part. So if I run this and I look at some images that were created, you'll see that there is a single image here. And then if I run the distributed, it will create 2 images, right? And the columns are the same. Let me change some values just so we see that. So if I make it now 4 qubits, I should see a different image. Yeah, so with 2 columns. And here, if you count, you so have 6 plus 2, 8, right? So f of 4 is 8, right? Out of 16 binary strings, 8 have no consecutive ones. And the next one should be 13. So let's test that. If I make this 5, and I can make it more columns so we can count. I can even make it 8 columns. And that is here. Yeah, so if you count 3, so we have 5 times 2 plus 3, which is 13. All right, and yeah, writing the circuit itself, you know, it's just state that apply, you know, and you put the gate. It's similar to Qiskit. You know, Qiskit applies gates to a circuit, right? We work directly with the state here. And really, you can have a DSL, like in Scala, we show the DSL that is nicer, a functional DSL. Okay, and the distributed, it's here on the slide. I won't run it, but there is a second method. I mentioned that the first was well, the first one was heuristic, so we had to come up with a, you know, good idea about the circuit. But if you want to automate, this is our latest paper. This was released last Thursday. You can see here Austin, Marco, and myself. Basically, we said if you have a formula for your Hamiltonian, then we can encode it efficiently. Right? So what is the Hamiltonian for this, that Ising model? If I want to count, so I map each configuration to the number of consecutive neighbors, you know, with the North Pole up, or in binary strings, consecutive pairs of 1. Right, and you can represent it as a sum of xi times xi plus 1. This product is non-zero only when both are 1. So you get basically the count, right? If one of them is 0, you'll get 0. So now we have a formula, and I won't go into the details. You know, you can read the paper about how it's implemented, but when we implement it, we get this picture that you see here when we visualize. So each column basically is, I should say prefix, is like the input. this is like the graph of a function. You have the input and the output on the vertical, but it's you know, flipped. In the paper, we actually did post-processing, so it really looks like a graph here. So numbers go up, the positive ones. But if you count, you see that we have 5 with 0 pairs, 2, 0, 1, 1, and 1, 1, 0. They have 1 pair of consecutive ones, and 1, 1, 1 has 2 pairs, right? And this is all encoded in the quantum state. Why is this useful? Once you have this in the quantum state, you can find the ones that have 0 pairs, right? Which is 1 level there, using quantum counting, right? Or if you want one of them, 1 ground state. This is an important problem in the icing model. Give me a ground state, right? And one of those 5 is a ground state. So you use the Grover search, and that's in our paper. You can get one of those ground states, right? But encoding it in the quantum state, this is useful. So the simulator basically helped a lot. I mean, I think we couldn't have done it without, you know, simulating to find all the, you know, the right things to do for that algorithm. So I'll run that. We call it test canonical because it's, one of the journalists is interesting. They didn't know what canonical is. They wrote a piece and they thought it was related to the canon law, you know, church or something. But in math, you have canonical forms, right? So it's a standard term. Okay, so now I'm looking for this, right? This is what we also have in the paper. And actually in the paper, if you look here, we have a picture running on the real computer. You get this gray image, right? And it's really close. Let me run a higher number just so you see if this works for any, okay, so I'm in the canonical. So I'll make it 4 now. Oh, sorry, it's already there. So now, see, you get, if you count, you'll get, yeah, whatever. So we are looking at level 0, which is this. So we have 1, 2, 3, 4, 5, 6, 7, 8, right? 5, we have 8 ground states for this icing model. Okay, any question before Vitaliy takes over to show how you make this scale? Right, so many times we are interested in just a few qubits, right? But if you really want, if you have a problem where you need to test a lot of qubits, then you need to distribute the computation, just like in animation, right? You'll have a farm of servers working on a problem. So if there are no questions, then Vitaliy, you can take over. I'll stop sharing.
Okay, I'm gonna share my screen and I have my keynote here. Okay, so can everybody see?
Yeah,
I can see as well.
Okay, cool. So I'll let you process what Konstantin just said, and I'm going to describe how we distribute this computation. So Konstantin described the domain of quantum simulator and the representation of quantum state using the color. Implementation is using binary tree and provides an example of distributing the computation using Go-routine. So it is easily mapped to the distributed computation using containers. We build on top of the concurrent example and create a distributed version of this simulator. In a distributed version, instead of Go-routines, we will use a containers, and we will assign a column in quantum state to a container. The name of the container is the prefix for that column, right? You remember the grid where you have rows and columns. So it will become a direct mapping. Or, as we say in distributed systems, it's simply sharding. We implemented a handful of APIs for the simulation. We use gRPC for the communication. So the screenshot here is an exact representation of the slimmed down simulator API. You have a couple of gates here. You have Hadamar, phase, control phase, RY, and control RY.
Yeah, this can be made more generic, where you pass a gate like we're doing in apply, but you know, for the time being, we just kind of hard coded these gates.
Yeah. So two important methods are get amplitude and set amplitude, right? So I know since all keys are fixed and there is no variation in the amount of data, and you saw the tree representation of it, this domain is perfect candidate for distributed scatter gatherer pattern using prefix sharding. The number of containers is the total number of prefixes or columns. So we will delegate the container management in this world to the Kubernetes, of course. And we implemented the custom resource definition using the Kube builder that basically gives you it provides like powerful libraries and tools to simplify building the Kubernetes APIs, right? So we have an abstraction, which is we call a server. Server takes in a mapped CRD request, let's say, which is simply a computation that you want to perform. The driver, which is the CRD in this case, will create a container topology based on the computation you provided, and then compute, store the results, and then destroy the containers after your computation. So there are a couple of requirements, of course. We need to apply one gate at a time, and we need to acknowledge before passing back the results that all the gates are applied. With Kubernetes, you know, like it gives us basically a platform for the container management state in easy, repeatable form, right? So, or you don't need to manage it manually in terms of retries and stuff like that. Yeah, so this is a visualization of Kube Builder. Now, we use Kubernetes-specific implementation of the amplitude store resolver, and you saw it in the previous slides with simple Go routines. So instead of the specific Go routine, we use a container with a prefix name. And here you see a random computation, and you see the container names with 000, 001, 0010, and so on and so forth, which is simply live sharding. Now, let's do a quick demo. So instead of using the CRD, I'm gonna demonstrate, because you're not gonna see much if I use the CRD. We split the computation in a couple of parts. One, using the simple Go client, I'll create, first I'll create the state. I'll run this command. Go run prefix demo, which will give me a which will create containers that will compute some columns, right? So each container here is a representation with a represented with a prefix name, and you will see a graphical representation of it right here, right? So I just created this this state that is able to accept some random gates computation, whatever I want to send in there. Let's look at the pods. Yeah, so the same pods are represented here. Now I'm gonna send a random computation, and this is just Rx. I'm applying Rx and control Rx. So yeah. And I'll tail the logs. So the computation have started. You see that the client for the distributed state send out those gates using those APIs that I showed earlier. And I'm applying Rx and control Rx. Now, once the computation is complete, we actually push the image in a remote store where you can, like look at it. But here in this demo, I'll just copy the image locally and show you how it looks. So it should show up here. Yep. So for each column, Konstantin showed this visualization earlier. For each column, we are creating, from each container, we are aggregating and collecting the image. And this is the full grid image. So I forgot how many, what is the matrix here? Let me see. So I used prefix of 3 with the bits 4. That's why it's a lot of colors.
Yeah, and we should say that if you have billions of amplitudes, you probably don't want to aggregate this on the client. You probably want, how do you simulate measurement, right? That's another question. And maybe you want the top probabilities. Maybe the single, if you have 1 million containers, you probably want the top in each container, and then you aggregate and see which one has the highest probability or something like that, right?
Yeah, and so those are the optimizations.
Yeah, with simulators, you have to choose what you want to simulate, right? But you really can customize your simulators to your simulator to the problem that you are trying to solve.
Any questions? I guess no questions.
I have gotten a couple questions in private if you are planning to share this anywhere on GitHub.
Yeah, that's a hard one for us, with lots of approvals and so on. That's why in our first paper, we actually put the code in the paper, and it became pretty long because that was, allowed. But so yeah, we don't know, Austin. Whatever we contribute to Qiskit, for example, that's easier because it's maintained by IBM, after that. And I guess, Marco, this is something that we can tackle later on.
Definitely. I think this would be like a great tool for the whole community. So we're very happy at JPMorgan Chase, a side comment, I joined the JPMorgan Chase in January of this year, and I came from IBM research. I spent 24 years as a researcher at IBM Watson Lab. So when I joined JPMorgan Chase, I was very excited, leading the FLAIR initiative, working on quantum computing, but I was not sure, JPMorgan Chase doesn't come across from the outside as a technology company, and it doesn't come across like as a leader in technology, because everybody thinks that JPMorgan Chase is a bank. So it was my surprise, and I was so happy to find a team with so much knowledge and expertise already in quantum computing, as you guys can see from these two presentations. We're writing papers together with Konstantin and Austin in particular, but soon the whole team, like Yuesan, Alex Batz, Jacob Mendel, there are many people that are here in this meeting. So
yeah, UA has a very well-known paper on option pricing.
Yes, exactly.
The investment bank had that. What's interesting is that for me, this is sort of the third revolution we're going through. Mobile was the first one. And we actually, always created intellectual property, and we were #1 from the beginning. We still are, for a reason, right? We couldn't make it public or talk about it, right? The same with the JavaScript. My team created the framework before React was there, right? And when I, went to QCon, I think it was, talked to the Netflix people, and we became convinced we need to do reactive. We created our own, and the same here. We have a lot of utilities, a lot of contributions internally, and the difference is now we can also share. So we'll see if we can go even.
Yes, exactly. So of course, being a bank, JPMorgan Chase has to obey certain regulations. So it's always a little difficult to share outside, every single thing that we're doing, but things are changing because the company understands that we are a research community, we have a research group. So we need to be part of the research community. And so we're happy to share, but I think people now understand how much knowledge and contributions are there in a JPMorgan Chase in the field of quantum computing, and we're very happy to be part of this community and share with all of you what we have done and learn from you as well, all the things that everybody else is doing.
Yeah, and also on a personal note, I was in math. I have a PhD in math, and then I switched to computers. When I went back to math, like 15 years later, I don't have the same tolerance for complex stuff, complex notation, superscripts and bolds and so on, and cursives, because it's hard to implement those in code. And if the goal is to put something in code, why not start with that simplicity and keep the simplicity? So that's why, you didn't see any unitaries, or matrix multiplication or linear algebra or high dimensional spaces and so on. Right?
Yeah.
Sums, high school math. That's our goal. Our first paper actually had an introduction, and the goal was to have a high school level introduction to quantum computing. And the simulator actually falls into that category, where it's so easy to implement it that a lot more people should play with simulators and quantum state.
Guys, yes, as the organizer, I can attest to the fact that, the moment open source people generally see something like this, they have double desire to play with this, because first of all, it's all familiar technology, right? This is a technology which everybody is learning. So I think it's an amazing feat, because you combine two things. You made Kubernetes a learning mechanism, which is truly awesome. So I bet if the community will appreciate, I understand how legal ramifications in finance are, but if there's anything we can help with, would be happy to. For instance, now since I'm at the Linux Foundation, and IBM is a member of Linux Foundation, maybe that's a mechanism, right? So one kind of way to basically put open source under Linux Foundation, and that actually makes it much easier. And there is a well-known way to make sure everybody's happy. So just an idea.
Definitely. So I also wanted to say I have a very similar background to Konstantin. So I also have a PhD in math, and for years and years I was like, why did I even bother to do all this math? Like if I was doing computer science, basically. Like, and so quantum computing is a good thing, you know, for me in particular, because I was finally able to use the math. But I also agree with Konstantin's point of view. Basically, there is no reason for people who are approaching quantum computing from different areas. You know, you don't have to have necessarily a PhD. You don't have to have a PhD in physics necessarily. That's like almost a misconception that pushes people away.
Yeah, but for the physical implementation of a quantum computer, you do need, right? So
sure. No, but for the work that we're doing.
For algorithms and applications,
exactly.
Yeah, it helps, right? But you don't really need even an advanced degree.
Yes, exactly. So for definitely for the work that we're doing at JPMorgan Chase, we're not really building a quantum computer. We're not in the field of quantum hardware. So having a foundation of physics helps for sure, because you can actually relate to certain concepts and so on. But personally, I really liked the presentations of both Konstantin and Vitaliy because of its simplicity. But the simplicity didn't take any rigor away. So it's still a rigorous approach without having to go through a difficult path. You can, for example, Konstantin mentioned, this is what a quantum state is. Like,
yeah, so the code doesn't lie. That's what developers say.
Yeah, my friend of mine at IBM used to say, code talks. So basically, like it's a rigorous approach. We didn't take anything, Konstantin didn't take anything away from this scientific precision. But on the other hand, the straightforward approach that we have seen in this presentation, I think is in a way even novel and very helpful for a lot of people, I think.
And it's true reactive, Alex. Super reactive.
No, this is just to clarify, you know, reactive foundation is not about just reactive applications. It's actually we see it as a cloud native applications foundation. So CNCF is cloud native computing foundation, which is an operator view, operating Kubernetes as a infrastructure for developers. But you guys actually using it, you know, as an application mechanism, right? So we really want kind of simple APIs if you're a developer, so you can scale your app without going into all the details.
This scales a specific use case, right? A quantum simulator.
Correct. Great. So any other questions, guys, for Konstantin and Vitaliy and Marco?
Hello, I would like to ask a question, Alexei.
Please.
Sure. Is there any additional advantages simulating ORK8 compared to other cluster orchestration managers like Mesos or Docker Swarm? Is it because of the good integration with, say, the cloud providers like GCP, AWS?
I mean, GCP and AWS AKS are both Kubernetes platforms, right? So we just, from the API perspective, it's easier to, I don't even think Mesos is in play. I mean, it was in play maybe 5 years ago, but I mean, the Cube became like a de facto standard for writing distributed application. It has a super clean, easy API. And I mentioned that we use Cube Builder, which is like a framework around the controllers. Writing pure controllers kind of, you know, like you need to understand the internals of the Kubernetes, but with the Cube Builder, it gives you like out of the box a lot of utilities.
Yeah, so if you want to make it dynamic, like you get a request, you create the containers on the fly, then you shut them down, right? You really need something like Kubernetes. Otherwise, you can just use Docker Compose, which is what I initially did before passing it to Vitaliy, right? So once you have your processes, you can, just use Docker Compose if you just want multiple servers.
And
right?
now
But,
with the latest versions, Docker actually supports native GPU computing, right? So if at some point we want to, multiply matrices, right? That's an option too.
Okay.
So I'm curious because I see Kubernetes and Docker's actually like a powerful tool, but what I was wondering, about the Google paper last year on the supremacy, and then IBM came up and said, well, no, we should be able to do this in 2 days on the Oak Ridge supercomputer. Of course, the Oak Ridge didn't bother to give them 2 days of time to run it. But I was wondering if one is using something like Kubernetes and trying to distribute networks around the world, would it be possible to try to validate or verify the IBM idea of solving the same problem? It may not be 2 days, it may be like a week, but basically the same problem that Google did back then through a quantum computer, second quantum computer, to validate whether IBM's statement is correct. Or what do you think about that?
This is a simulator. It's not a real computer. It's a simulation of the quantum.
Right. Yeah, so I think IBM used some kind of HPC to simulate the 53 qubits that Google used, right? And
no, actually it was quantum processors, was the Sycamore quantum processor that they did the execution for 2 minutes. They held it and they generated a random strings. And they claim that basically this type of computations are practically impossible nowadays.
Right, but
the
IBM,
argument was based
I think
on
IBM
the memory.
I think IBM duplicated the computation classically with a simulator. So they said even the quantum computation, we can simulate in 2 days and a half. Right? You don't even
that's what they proposed, but they didn't do the calculation.
Yeah.
So the thing is that it's still kind of hanging out there. Is it possible or not? And I guess Oak Ridge wouldn't give their computer for 2 days to be running just for that. But the alternatives are using a distributed network, maybe not 2 days, maybe a week, but still, if you can validate this idea that you can distribute it in a way that you can do it in a feasible time, that's the question whether it's doable or not.
So sorry for, so first of all, a couple of things. I don't think IBM actually implemented their solution. I think it was a theoretical stipulation, like a theoretical hypothesis that based on certain calculations, they knew that they hypothesized that the same computation, the same problem solved by Google could be solved classically even more efficiently than, even faster than the quantum computer. But I don't think their solution was based on simulating a quantum computer. So in other words, for example, there are certain problems that can be solved with a quantum computer and with a classical computer, but the classical algorithm is different from the quantum algorithm.
So if anyone who is at IBM, maybe they can, but what I read was, the point was, even the quantum computation as is, I can simulate it in 2 days and a half, right? So it cannot be, or at least one of the points, maybe both points were made.
Well, the estimate that Google came up was a few thousand years, but they were relying that this would be done actually in the memory of the computer. And IBM said, well, you don't need to do everything in the memory. You can distribute it on a distributed machine. And you can use hard disks and other things, so you don't need all this memory to run it.
Yeah, but if you want to add 20 qubits, that would, that's what we calculated. Just the power, you take the log base 2, right? Then you need 1 million. You take the power of 2, right? You need 1 million containers, right? So it's a matter of can you handle, can you handle that? Can you even, the price is the problem, right? 1 million containers.
But you know, we have this kind of SETI at home programs. I mean, there are a variety of others where the people will say, okay, I will allow my ideal CPU and GPUs to be used if somebody wants. And that's a question of actually somebody setting up a reasonable network and Kubernetes cluster to be pushed on different places and to perform the activities. Of course, it's kind of a enormous work still, but
yeah. So when we talk to other people into simulators, they assume you have to multiply matrices and use GPUs and swap numbers and so on. And that was one of the points. You actually don't, right? You only need to use 2 by 2 matrices. That's what they are. That formula of a single qubit gate is a 2 by 2 matrix. Right? And that's all we need. And it's a perfectly balanced, like we said, you have 2 servers talking to each other for a while. One of them can do half of the computations because it gets the numbers from the other and calculates both numbers so they can send them back, you know, and say, here are your numbers. And the other server can do the other half, right? So it's a really perfectly balanced computation. You couldn't hope for a better, like Alexis said, you know, even for teaching Kubernetes, I think it's one of the best domains.
Great, you know, and actually, if I might add something as kind of a driver for Morgan Chase to open source it, right? Computer science are very good at benchmarking. So if they have something, I think Veselin has a great point, because if there is something to distribute, right, then you can do a lot of fun things. For instance, you can ask GCP and AWS to see who can simulate the biggest quantum computation, and then you will get your machines for free, most likely. You can get credits. You can, I mean, that actually becomes a very interesting benchmark, right? It's a hard distributed problem, which essentially you can spend any time on running, and so you know, that would be super interesting to try and pit one, you know, Azure against GCP and AWS and see who can perform as a whole, right, better.
Yeah, I mean, you can make it a service really if you want to, but Google has its own simulator, I bet, right? So I don't know how they do it, but I'm sure they
do it better with less cost.
Yes. For themselves, of course, right? But I think we've seen that community, like if community puts its mind to something, it usually does the best job. So yeah, I'd be super, you know, happy to help you guys.
Yeah, well, what I'm hoping is that people who understand combinatorics, for example, they will see they can do quantum computing because they work with binary strings, right? You don't need or just computer scientists. You need you know, simple concepts. And then once more people jump in, you have, you know, a bigger community.
Exactly.
And from a computational complexity perspective, also what we might want to keep in mind is that adding 1 qubit just to the 53 or whatever amount was used by this Google supremacy experiment, right? We add 1 qubit that doubles our space. That means you would be for a classical simulator, or let it be a network of computer, you would have to double your classical computing power. Now the number of workstations on this planet is finite. At some point, the complexity of exponential versus polynomial runtime, you can't catch up with anymore. This is why soon, when we do have machines with high enough fidelity that we can use a few more qubits to do some computations, we'll soon run into a situation where it's really getting really hard to build simulators to do the verification. Now add another 10 qubits and it's out of the possibilities of anything we can do. It's just now that the exponential complexity versus polynomial runtime algorithms. Unless we find algorithms that run in polynomial time that we don't know about yet. So there's a lot of research to be done on that field, I'm sure.
Right. So somewhere around 30 qubits, 32 qubits, maybe we know we can do, and it's useful. Right. Going higher, you may have reasons to do it, right? But it may not be a real reason to spend the money. Right? Like you said, you double the compute with every qubit, right? So to add 10 qubits, you need 1,000 servers, right? So let's say we can manage 20. I think we tried, depends on the computation, but we tried 24, 26 on a single machine. And then you, to add 10 more, you need 1,024 containers, right? And then 2,000, 4,000, right? And so on. So yeah, at some point it becomes prohibitive.
Yeah, I agree, it explodes. But the good thing is that we can do at small spaces validations. And once we are confident in the algorithms, then we can just trust the results in the impossible spaces where we cannot do classical calculations.
Right.
Thanks, guys. I think we have the unconference part, and I think we have at least one talk by Veselin actually submitted. I want to see if anybody else here wants to present, or they want to ask kind of for a small explanation of some topic. So we can have two kind of things, right? We can have folks giving lightning talks for a few minutes, maybe announcing projects, inviting collaborators. And another one, kind of if folks want to learn something, kind of one-on-one overview of a field, they can ask if anybody here can teach us that. So I'm opening the floor for this. If I think we have one talk by Veselin, right, which will go first, then I want to understand if anybody else wants to speak. And this is very informal, no preparation necessary. As just as we were talking about, Kubernetes scalability, in the same fashion, we can discuss other topics. So just checking if anybody wants, just say so. Interesting. Yeah. Okay. So I don't see anybody yet volunteering. So Veselin, it's all yours then. And if people want to speak after Veselin, let us know. So take it away.
Okay. So should I share my screen and then can I do that?
Yeah.
Okay. Yeah, I can do that. The slides are also online if somebody wants to look at it. And by the way, for those of us that are in California, I think we just had an earthquake here.
Oh, really?
Yeah.
Maybe that's why internet is so slow for me. Hope not.
Good to see you still have Wi-Fi connection. That's a good sign.
Yeah.
Yeah.
So I'm starting my screen share. It says loading. Do you see my screen?
Yep, I see it here.
Okay. So thank you, everyone, and thank you for the opportunity to actually kind of present this conceptual idea of quantum computing for all. I like the type of meetups you're running here, Alex, and I think this is well aligned with what I'm trying to do in the long run. So this is an idea where we try to build community around Merced, because UC Merced is the newest UC campus here in Merced in California. But there is also the Stanislaus State and Fresno State, which is the California State University System Educational in the area. And these are like a half an hour from each other from Merced, with additional community colleges, like 5 community colleges. So I wanted to just share with you the local ecosystem and show that there is a lot of opportunity here if people are interested to engage. So a little bit about Merced. You can see it, it's practically in the center of California. If you zoom in the map, it's north from Sacramento. I mean, it's close to San Francisco, Monterey, almost everything in Northern California, you can reach it within 2 to 3 hours drive. So as I mentioned, there are different software developers.
I think we lost the audio.
No, the earthquake.
Yeah,
no.
I think he may have been dropped.
Looks like we lost Veselin, guys.
Can you hear me?
Yeah, we lost your screen for a moment.
Okay. Yeah, I think we noticed today a few times the system was logging again and again. Do you see my screen now?
I don't see your screen, but you can just speak and while it is connecting, because we can at least hear you.
Okay. Definitely there are problems with the network on my side.
Okay, we can see you. And
can you hear me?
Yep, I can hear you. Hope others can do too.
Yeah.
Okay, and it says it's loading the presentation. Can you see now?
I cannot.
No.
It's about California Central Valley, some of the software developer workplaces around. Okay, can you hear and see the picture?
We can only hear you. I cannot see. Let me see. I'll make you co-host. Maybe that will help you present.
It's very unstable. Yeah.
Those Californian developments.
Yes.
They occupy all the bandwidth. You're saying they occupy all the bandwidth?
Right. So Veselin, I propose that, instead of sharing, just tell us, and hopefully, okay, you started screen sharing. Let's try it again and see if it fails again. You can just speak without the screen sharing.
Okay, I'm starting the screen sharing.
Meanwhile, I looked up Merced. It is indeed actually not far. It's about an hour and a half from SF. So that's indeed centrally located.
Yeah, we have our airports around here too. So do you see now the screen?
Yeah, I can see that.
Okay. So what I wanted to point out here is that there is also software developers. What I hear, many are moving to Modesto because it's much more cheaper and attractive to live and have your team in Modesto, although your clients are in San Francisco. In Fresno, there is actually a very big company, Bitwise, that is very active. They're building their own software developers. And I like their approach to teaching computer programming because it's more like the apprenticeship. And that's where I realized that it's, although for some of us, quantum mechanics took years and it's a lot of passion. But now with IBM, Google, I mean, different quantum companies, it could be something that people can program and do on their own, and they don't have to spend years and years doing it the standard way. So idea is to build some connections between industry and academia, setting up kind of dual talks where people from industry would give a talk and then people from academia would give a talk. And that's why Merced is very nicely located. We have like the 4 campuses of University of California nearby. Then we have another 5 down south. This means that one can organize workshops in the Northern California in the different hubs. And these workshops could be kind of combination of this business academia interactions. So that was our idea. We were trying to organize such meetings. And now, I don't know, probably it's one of the hopefully positive side effects of the pandemic is that people would realize, oh, I can actually do this online. So I can finish with kind of list of people that are involved around here. Tom Carter, he is the chairman of the computer science department at Stanislaus. We have Jay Sharpie, Liliana Davila, she's engineer, Chin Chen, and a few other faculties from UC Merced. Douglas Singleton, he is from Fresno State, and we have few others, mathematicians and physics people there. Also in Fresno, they have a business school that is more active. So our idea is to involve students from the universities to assist in the preparation and the talks that would be given by industry and academia people, and then business students to approach the logistics with the purpose of building startups that would be eventually doing a hackathons and growing into some business ideas related to quantum computing. And I want to finish with UC Merced Venture Lab. This is kind of an ecosystem that is really supporting all these efforts. And if you want to communicate further, feel free to connect with me on LinkedIn or send me email. And let me know if you have any questions or comments. I'm open for growing this kind of idea and turning it into a reality. Thank you for your attention.
Thank you, Veselin. That's a great review of a local ecosystem. You know, initially we wanted to call this Quantum West. We opened it to the world due to kind of global nature of online, but we're really interested in building up the West Coast community. So that's real helpful. I hope once we resume physical meetings, the plan is to meet, you know, in Berkeley and Merced and Stanford. I think it would be really, you know, Livermore. It would be great to connect local ecosystems. So thank you so much.
Yeah, thank you.
Anybody else would like to do a lightning talk? Not yet. Great. Well, thank you so much. It was a great second meeting for Quantum Conversations. We plan to keep going on a roughly monthly basis. We'll put the video shortly on YouTube, and the link will be also on Quantum SV. And if you'd like to present at one of the next meetings, please email me, and hope to see you guys all again. Thank you so much.
Thank you.
Yeah. Thanks, guys.
Thank you.
Thanks.
That was awesome.
Bye. Have a good day.